All right, so let's continue where we left off. Okay. All right. So here's a problem where we might want to use or could use some of those counting methods, like the fundamental counting principle, or we might be able to use the like combinations or permutations to try to figure out the answer to these questions. Okay, so here we have two integers that are randomly selected from the digits 1 through 9. Then we're going to add them up together. Right, and we want to know the probability that the sum is going to turn out to be 11. And then we have this added condition that they are selected without replacement. So without replacement just means this. Think about picking those numbers. Think about those numbers being on little slips of paper in a bag. You're going to reach in and pick one. Whichever one you pick just stays out. So it's not being replaced. So it's not available to be selected the second time. So if you think about that, and you think about the fundamental counting principle, aren't there 9 possible digits you could pick for the first number? But then after that, don't you just have 8 left? Because whichever one you pick the first time, it's not available for the second selection. So that means you have 72 possible selections of two integers, 72 possible ones, because you can't select the same one twice. Okay. Now, what we want to know is what's the probability that their sum is going to turn out to be 11. So then we have to think a little bit about this. So let's think about this 9 times 8 and what it means and where it came from. We're not going to actually draw out everything, but I just want to give you a sense of it. So when we picked that first one, the reason 9 was there is because we could have selected any of these digits for the first one, couldn't we? Any of those. But when we go to pick the next one, if the first number was a 1, then the next one I picked couldn't be a 1. So it'd be like 2 through 9. Okay? And then if I had a 1 to start with, then it could be paired up with a 2 or a 3 or a 4 all the way to 9, right? But if I picked a 2 to start with, then it could be paired up with a 1, could not be paired up with a 2, so 22, 3, and then 2, 4, 2, 5, all the way down to 2, 9. See how there's 8 here, and 8 here, and 8 in each of those lists, right? So 31 all the way through 39, right? 41 through 49, you just wouldn't have, there'd be no 33, there'd be no 44, and so on. But we'd have these possibilities here, okay? So I just want to have you really see confidently why we get what we get. So let me just get you to think about this for a minute. Let me get these on here. I don't know why I did that. 71 through 79, 81 through 89, and then I'd have 91 through 99, okay? And remember, there's going to be 8 possibilities there. The only one that's missing would be when a repeated digit was used. All right. So we want the probability their sum is going to be 11. If you look at that first column, this one here, none of those add up to be 11, right? But in the second column, 29 would. In the third column, I'd have one possibility, 38. In the fourth column, I'd have one possibility, that would be 47. In the column under the 5, the fifth column, I would have 56, then 65, and then 74, and then 83, and then 92. So see how there'd be 1, 2, 3, 4, 5, 6, 7, 8. So if I were thinking about this, I could just think about all the possibilities, which would be these 72 possibilities, 8 in each of these columns, and then 9 columns times 8 would give me the 72 possibilities. Then I could think, well, none of these Okay? And then one possibility out of each of these other columns would add up to be 11. And then I could say 8 out of 72 and get 1 over 9. Now, if I wanted to do it without looking at that whole list, I would just have, if I wanted to get that, let me write that over here. So, to get the answer, I could have been thinking that there are 8 outcomes that would add up to be 11 out of the 72 outcomes, and then simplify it. To come up with these guys right here without actually drawing this out, I could have just thought about the fact that 2 with 9, 3 with 8, 4 with 7. I could have thought about that. Let me go ahead and go over here. And then 6 with 5, 7 with 4, 8 with 3, 9 with 2. There's those 8 possibilities that would make the numerator. So 8 on top, 72 on the bottom, and I'd get 1/9. Okay. All right, now you can also do what looks like the fundamental counting principle, sort of what we did with passwords earlier. You kind of think about it that way. Another possibility would be to say to yourself, 1 can't be paired up with any number. If I select a 1, there's no way of getting 11. So some people might say there are 8 numbers to choose from for the first digit out of those 9. If you want the sum to be 11, you couldn't choose a 1. And then when you go to choose your second digit, you only have 1 that can match up with it. So once you've picked the first digit, there's only 1 precise number that you can select for your second digit, and there's only 8 numbers left. And so that's another way to get 8 out of 72. Okay? So you didn't really have to draw the tree, but you did have to kind of visualize what's going on. And so sometimes the tree just helps me get that sense of what my outcomes are and how to approach the problem, because this is not an obvious problem. You had to kind of reason through a couple of aspects of it. So the final answer would turn out to be 1/9 when you're finished. Okay? And by having all the outcomes kind of pictured like that, that helps me be able to answer the question and feel confident about my answer. Okay? All right, let's try another one. On this one, we got a student who's going to take 3 courses, randomly selecting them from a list of 12. 5 of them are science classes, and the question is, what's the likelihood that all of them will be science classes? Okay, so it's like we have 12 to choose from in the first spot. Then there'd be 11 to choose from in the second spot. So 12 to choose from. Then there'd be 11 to choose from, and then 10 to choose from for getting all the possible selections of 3 courses. Okay. Now, when we do it like that, then you're looking at like science, maybe it's biology, chemistry, physics. When you write it this way, that's like making it where if you did biology, chemistry, physics versus physics, chemistry, biology, those would be counted as separate things. Okay? So that seems like that would be a problem, that you just want to know the group of 3 courses, not the order doesn't really matter. So you may think you couldn't do that, but you may be thinking it's more of a permutation problem, like 12 courses, a combinations problem, not a permutations problem. And do 12 courses, choose 3, which doesn't just do 12 times 11 times 10. It also divides by the number of ways you could arrange any 3 courses. So you might be thinking that. Okay, so 12 courses, choose 3 would be your denominator. How many groups of 3 courses you could get out of those 12. The numerator would be how many groups of 3 courses you could get out of those 5 science courses. You want the probability of selecting a science course. So the numerator would be the ways of selecting a group of 3 science classes. And then you could work that out. Well, 5 choose 3 turns out to be, oops, forgot to put the second number in, hold on. Turns out to be 10, right? And 12 choose 3 is 220. And then if we divided both of those by 10, we'd get 1 out of 22. All right, now it's kind of interesting though. If I had done it like it was a permutation, like did it more like this, which is really a permutation idea, did 12 times 11 times 10, and then on top thought about 5 science classes to start with, then 4, then 3, that would also work, okay, even though it doesn't seem to be the right thinking, since you would want these to be considered the same group. That's why the C would be feel more appropriate. But if I had done it like this right here, then when I do that, it winds up reducing to be the same thing anyway, in this case, right? Because we wind up getting 1 out of 22 on that one. So it turns out that it would have worked if I had used this concept right here, which is really like P, 5 classes, choosing 3 of them, over 12 classes, choosing 3 of them, but using the permutation feature. Turns out to be the same, but it has to do with the fact that you're actually dividing on this. And so it winds up being equivalent. That winds up equaling the same thing as this one, okay, because of the division component. I actually don't use either the combinations feature or the permutations feature when I think about it. I'm just thinking about it. There are 5 science classes to choose from out of 12 to start with. Then I'm down to 4 science classes out of 11 courses all total. And then I'm down to 3 science classes out of 10. And then I just work that out and get my 60 over 1320 and simplify until I get 1 over 22. That's actually a nice intuitive way to do it that doesn't really get you bogged down into the idea of whether permutations or combinations would be better. Okay. All right, now let's think about number 7. Here, they're talking about something called a trifecta. So that's a horse race term, horse racing term. All right, if you pick the horse you think is going to win, the one you think is going to place, and the one you think is going to show. So that's like first, second, third place winners. And you pick them, you select them in a certain order. So you're going to say who won, who's second, and who's third. So we're looking at what's the probability of having selected the winner. If there's 5 horses of equal ability, and she just kind of randomly selects, makes a selection, what's the likelihood that she's going to be a winner? So when you're thinking about that, it's like the number of possible first, second, and third place combinations, the number of ways you can choose these 5 horses, right? I could pick A, B, and C, or I could pick, B, A, and C, which would be a different way of selecting first, second, and third places. If I wanted to know all the different ways of selecting 3 horses in the correct order out of those 5, that would be a permutation, wouldn't it? Since these are really different, we'd want to count those separate. So there's 5 horses, you're picking 3, and we're using the P feature because ABC and BAC would turn out to be the same thing. So those are all the possible selections of first, second, and third place winners. And only one of them is a winner. So we could do that. We could take 1 divided by the number of ways of arranging 3 horses. Okay, the permutation feature. Okay, so let me take 5 and do the permutation feature with a 5 and then NPR 3, which would be 60 and only one of those would be the winner. So you'd have a 1 out of 60 chance of being a winner. Okay? All right, now, this next little chunk is really trying to get at the meaning of probability, like what it's really saying and what it's not saying. All right, so let's take a look at this idea. Law of large numbers, or the law of averages. So the more you repeat an experiment, like tossing a cup, the proportion of outcomes that are favorable to a particular event will come closer and closer to the theoretical probability of that event. All right, let me use something that has a good, clear theoretical probability. So rather than tossing a cup, think about rolling a die. So if I roll a die, just a lot of times, the proportion of outcomes favorable to a particular event, like getting a 2. Say I'm rolling a die as my experiment example. I'm going to do it a bunch of times, and then I'm going to look at the number of times the outcome was a 2. What we're saying is, the more you do that, the more you roll the die and check on whether you got a 2 or not and determine the probability, the closer that you're going to get to the theoretical probability of the event. So the theoretical probability that would be that you have a 1 out of 6 chance. Okay? But a theoretical probability really doesn't say what's going to happen if you only do the experiment twice. It's only telling you about the proportion of successes, the number of times you get a 2 if you did this 1,000,000 times. Okay, so it's really telling you the proportion of successes you would expect in the long run. Okay, so think about it. If you roll a die, you have a 1 out of 6 chance theoretically of getting a 2, but the first time you roll the die, you might have gotten a 1. Okay, so if you only rolled it once, you got a 2 no times out of that one time you rolled it. Now you might roll the die 10 times, and maybe you got a 2 twice in those 10 times. Then the experimental probability would have been 1 out of 5. Doesn't match the theoretical probability because you've only rolled the die 10 times. I mean, you could have gotten a 2 every single time. A 2, you might have been lucky and got a 2 every single time. Then the probability in those 10 times you rolled the die, if you got a 2 every time, then the probability would have been 1, right? So the actual probability you got for a certain number of times you did an experiment might not equal the theoretical probability. What that theoretical probability is really saying is that if you rolled the die a ton of millions and millions of times and looked at the probability, it would be approaching 1/6. So these repeated experiments provides an empirical probability for an event. And then using inductive reasoning, that's reasoning from examples, using that type of reasoning, that gives you an estimate of the event's theoretical probability. And the more you repeat the experiment, the more reliable that estimate is going to be. Okay? Also, we might have an established theoretical probability. Like when we're rolling a die, okay, we know the chance of getting a particular outcome is 1 out of 6. Where if we're tossing a coin, the theoretical probability of getting heads versus tails would be 1 out of 2. Okay, so an established theoretical probability for an event enables us by deductive reasoning That is reasoning from something known to predict how many times you could expect a certain event, like if the event was getting a 2, that you could expect to get a 2 if you rolled the die 20 times. Okay? The prediction would be more accurate the more that you perform the experiment. Okay? So let's look at this situation here. All right, so here we have a gambler that's at a roulette table. So a roulette table is a wheel that has all these spaces around it that hold a ball, that can hold a ball. And as that wheel spins, the ball moves and finally lands in a particular space. And the spaces around the wheel are red, black, and green. And we're told there's 18 red ones, 18 black ones, and 2 green spaces on the wheel. And each of those spaces, it would be equally likely, the ball technically should be equally likely, have an equally likely chance of landing in any one of those spaces. So the theoretical probability of the ball landing on red would be 18, because there's 18 red spaces, out of the 18 plus 18 plus 2. So 18 plus 18 plus 2 would be 38 out of the 38 spaces on the wheel. And that would simplify to be 9 out of 19. And the decimal for that would be 0.473684211 about. Okay. So the next question here says, based on the theoretical probability, knowing that there's a 9 out of 19 chance, theoretically, of landing on red, how many times to the nearest whole number would you expect to land on red if you spun the wheel 20 times? Okay. So we could take our probability, 9 out of 19, multiply by the 20 times we're going to perform the experiment, and that would give us an estimate of how often that should happen. So that would be 180 over 19, and when I do that, 180 divided by 19, why does that say 9? It shouldn't. Something's wrong. That would turn out to be like 9 about, or exactly, maybe about 9.47. So it would wind up, something's wrong with the setting on my calculator, but anyway, I'm trying to fix it real quick. It's like it's rounding when I don't want it to. Anyway, and so when I get that 9.47, then I'm thinking, oh, so I might expect it to land on red 9 times. So about 9 times. Okay. Well, what if the ball actually landed on red 14 times out of the last 20? Okay. We would have expected it to land about 9 times, but it landed 14 times out of the last 20. The empirical probability then would have been 14 out of 20. When you divide by 2, that's 7 out of 10. Would be 7 out of 10. Okay. Which is way higher. Okay. That's 0.7, isn't it? Okay. Rather than 0.47 or whatever we had earlier. Okay. So does the result here that we got here, that the ball, we would expect it to land on red about 9 times, and it landed 14 times, does that mean it's rigged? Does that mean the roulette wheel is not functioning properly? Okay. Should have said in part C. Okay. So the fact it landed 14 times out of 20 and we'd only have expected it to land 9 times might make you think there's something wrong with the wheel. But because 20 is only a few times, you would say no, too few spins. Okay. In the long run, we would expect it to land on red about, move that out of the way, about 9 out of every 19 times. Okay. In the long run, like if we spun the spinner millions of times, and I guarantee you that's probably something that casino is going to keep track of, and maybe some of the agencies regulating casinos probably look at that, is in the long run, what did the data show? Okay, because if you don't wind up having the actual data match the theoretical probability of each of these, this would be 18 out of 38. This theoretical probability, 18 out of 38, and then 2 green, chance of getting green would be 2 out of 38. If the actual probability didn't come close to those when the spinner was spun millions of times, okay, then you would be suspicious that the wheel might not be functioning properly. Okay?